Chapter 3, Internal Energy and Enthalpy. Section 3.5, Internal Energy of Reaction and Hess's Law. The internal energy of reaction is the internal energy of the products minus the internal energy of reactants. The products are the final state of the chemical system. The reactants are the initial state of the chemical system. For example, if we look at this reaction with N2O4 as the reactant, NO2 as the product, then the internal energy of reaction is equal to 2 moles of NO2 minus the internal energy of 1 mole N2O4. However, this example is problematic because if you look at these coefficients 1 and 2, they are not really the number of moles. They only reflect the ratio between the number of moles, not the actual number of moles. Therefore, we say the internal energy of reaction of this N2O4 to 2NO2 should be defined as, again, the internal energy of 2 moles of NO2 minus the internal energy of 1 mole N2O4. But then we need to add these 3 words, per mole reaction. And now this definition is more rigorous. The SI unit of the internal energy of reaction thus is joule per mole. Again, over here you see per mole reaction. So the SI unit is joule per mole. However, if we use joule per mole for typical chemical reactions, the corresponding numerical value will be very large, usually in the order of thousands, tens of thousands, or even hundreds of thousands. Therefore, the more commonly used unit is kilojoule per mole, just for convenience. And then we have usually several kilojoule per mole, tens of kilojoule per mole, or at most, several hundred or thousand kilojoule per mole. And similarly, the enthalpy of reaction is simply the enthalpy of the products minus the enthalpy of the reactants per mole reaction. Now let's look at this as example. You can say, well, the enthalpy of reaction is the enthalpy of 1 mole water minus the enthalpy of 1 mole H2, and then minus the enthalpy of half a mole of O2, and then per mole reaction. Again, the SI unit of the enthalpy of reaction is simply joule per mole, but we often use kilojoule per mole for convenience. Now let's look at the standard enthalpy of reaction for this H2 plus 1/2 O2 to become water at room temperature. It's negative 285,800 joule per mole. So this is not very convenient. That's why we usually say negative 285.8 kilojoule per mole. Now what if we double the coefficients? When we double the coefficients, we double this numerical value to negative 571.6 kilojoule per mole. What if we flip the direction of the reaction? So over here we have water on the right hand side. What if we write water on the left hand side, H2 and O2 on the right hand side? Then we need to change the sign for the enthalpy of reaction. Now it's positive 571.6. This is dictated by the Hess's law. Now let's look at the internal energy change of reaction. It's actually equal to the heat flow of the reaction at constant temperature and volume condition. And now if we look at the enthalpy of reaction, it's equal to the heat flow of the reaction at constant temperature and pressure condition. So now let's review the expression of du. du is delta U over delta T times dt plus delta U over delta V times dV. And we have this equation only if there's no chemical reactions. And at constant temperature and volume, if there's no chemical reaction, dt is 0, dV is 0, and therefore du is 0. But what if there's a chemical change? Then du is non-zero, even if T and V are constant. This is because at the beginning we have reactants, at the end we have products. They are different. Therefore, there is some internal energy change, even if temperature and volume are constant. And if we integrate this du, we get delta U reaction. This is equal to Q reaction plus W reaction. If the volume of the system is constant, there's no expansion, there's no compression, this part is 0, and therefore we have delta U of the reaction is equal to Q reaction. Similarly, we can write dH in terms of dt and dP, assuming H is a function of T and P. So if we just look at this equation, if temperature is constant, pressure is constant, then H is a constant. If there's no chemical reaction, but what if there is chemical change? The initial state is the reactants, the final state is the products. Therefore, dH is non-zero, even if temperature and pressure are held constant. And again, we can integrate this dH. This is delta H reaction. It can be expanded as U plus PV. That's just the definition of H. H is defined to be U plus PV. And then we have this equation. This is because delta U is Q plus W. This is Q and this is W. W is negative P delta V under constant barrier condition. And what about this delta PV? Delta PV is actually P delta V, only because this is isobaric, P is constant. Therefore, delta PV is equal to P delta V. And this to cancel, we just showed this delta H of the reaction is Q of reaction. And over here, just a reminder, when we have this in kilojoule per mole, this has to be kilojoule per mole. This is Q reaction per mole reaction. Exothermic reactions releases heat. Q reaction is less than 0. Endothermic reactions absorb heat, and Q reaction is greater than 0. And in the end, is Q reaction equal to delta U of the reaction or delta H of the reaction? We don't know. It depends on the experimental condition. If the chemical reaction proceeds at constant temperature and volume, then Q reaction is delta U of the reaction. If the reaction proceeds under constant temperature and pressure condition, then Q of the reaction is delta H of the reaction. In general chemistry, Hess's law is used to calculate the enthalpy change of a reaction that can be expressed as a linear combination of multiple reactions. Hess's law is exact because enthalpy is a state function. The enthalpy difference between a set of products and a set of reactants is the same regardless of the process in which the reactants is converted to the products. For the same reason, Hess's law can be used to calculate the change of any other state functions. It does not have to be enthalpy, because internal energy is a state function, G and A are state functions, entropy is a state function, temperature, pressure, volume are state functions. Actually, Hess's law can be used for all these other state functions. For example, the internal energy of reaction of A to 2C can be calculated given the internal energy of reaction of this from A to 2B and then from C to B. Okay, we're going to treat those reactions as if they were numbers, and then we can do addition, we can do subtraction, we can multiply those reactions by numbers. Alright, so for example, from A to 2B, if the internal energy of reaction is 20 kilojoule per mole, we'll put it here. And from C to B, it's 30. Therefore, from B to C, if we reverse this reaction, it should be negative 30. That's why you see a negative sign here. From B to C, it's negative 30. What if it's 2B to 2C? It's negative 2 times 30. Therefore, we have these two reactions. And then if we sum up these two reactions as if they were numbers, we can get the sum. What's the sum? The sum is we just combine the left hand side, which is A plus 2B. We combine the right hand side, it's 2B plus 2C. Note this 2B appears on the left hand side and also on the right hand side. They cancel. Therefore, the sum of these two reactions is from A to 2C. And correspondingly, the internal energy of reaction is this 20 minus 2 times 30, which is negative 40. Again, I really want to emphasize this. Hess's law is not about just enthalpy. You can apply Hess's law to any state functions, PV, TS, UH, because the change of a state function depends only on the initial state and final state. How the system reaches from the initial state to the final state is irrelevant if we just want to compute the change of a state function.